This is for our FSC 100 class at ASU. The year is 2019. We're freshman class 2023 for Mr. Newby, and we're Team 9. My name is Corbin Cregan.
I'm Sadie Rosenbaum.
I'm Dominic Lopez.
And I'm Jake Pimberla. So we noticed that there were two different things that people would use for batting practice in terms of baseball. The first would be a human pitcher, and the second would be a pitching machine. The problem with a human pitcher is that after a certain number of pitches, you can't throw anymore for a certain number of days because of the wear and stress on your elbow and shoulder. The problem with a pitching machine is it's repetitive, and pretty much anyone off the street can just start knocking balls into the yard if you keep putting it in the same place at the same speed. So we started looking into it and seeing if there were pitching machines that were variable, and it turned out that already existed, but they had to be manually turned or manually adjusted so the batter would know it was coming. So what we set out to do was to create a new adaptive pitching machine that would automatically simulate not one pitch or one kind of pitch, but an entire at-bat featuring fastballs, curveballs, sliders, knuckleballs, anything we could.
So our target customers for this project were any teams that played baseball, including like the MLB, college baseball teams, high school baseball teams, or just any baseball teams in general.
The requirements were to throw 3 types of pitches: fastball, curveball, and gutter, or any variation of the 3. Another requirement was to detect the ball crossing the plate and also the bat crossing the plate. And the third requirement, we react to calls made by the sensors.
The criteria that we had was cost, aesthetic, and functionality. Cost being because not every high school team can afford a $4,000 pitching machine. The aesthetics because it needed to look good while we're using it. And the functionality is of course necessary for the pitching machine.
These are our main driver motors. These are kind of the heart and soul of the machine. They're 6-volt motors, and they serve to just throw the ball forward. Those are connected to the servo motors. If it'll load. These servo motors have a little pin up here which is connected to the side of the motor, and those serve to change the angle of attack of the motor to get the ball to come out at a different rate of rotation. And what that effectively does is it changes the flight path of the ball as it cuts through the atmosphere. So if it'll load. This is kind of our main assembly bay. It's a little bit upside down, or a lot upside down. But so it's angled just to give us a decent angle of attack as far as the ball itself goes. And then here it is. So here's the top here. This cutout is where the motors and everything go, and that serves to give it enough clearance for the ball to actually pass through the flywheels, which are connected to the ends of the motors. And then on the ground, we have, here it is, we have a plate. And on the plate is our Arduino and all of our sensors, which serve for the electrical components, which I'm not going to go over right now because I was instructed not to. But so here's home plate. This rests on the floor and has cables running up to the motors and servos and tells them what to do in accordance with which pitch needs to be thrown next. That should be good, right? So, as mentioned in the last video, these are our flywheel driver motors and the flywheels themselves, which are, they're kind of soft to allow better grip on the ball because more surface area equals more grip. The ball passes through here, and then these are what makes this different from a normal pitching machine is the servo motors here. So some pitching machines have the option to kind of angle these to create a curveball effect, but the coach has to go in and do it manually, and the batter knows it's coming, which kind of defeats the purpose of a curveball. So what we did was we linked the servos to home plate and an array of sensors, which we'll explain in a different video or something, I don't know. So these all the ball or bat comes through here, and based on the way that happens, the machine knows which pitch it's throwing next, but the batter doesn't, and that's why it's a more effective tool for training batters. So the servos are powered by the main board, but the motors themselves are running off of 12 volts each, just to keep them running at a constant speed, because enough speed adjustment happens with the change in contact area with the ball coming through.
Go.
this is a 9-volt battery that's going to allow the Arduino to run autonomously without the use of a laptop. This is the central motherboard for our entire system. It supplies power and digital read-ins and readouts to everything else on the board. This is our sensor module right here. This is what's allowing us to know if a batter swung or if a ball crossed over the plate. And then that had a power issue, so we're using a second Arduino to modulate power that runs to that, and that's the only reason this thing is here. It's just a power modulator. These two really long cables here run up to our pitching unit itself, and these two control the servos. So when a certain kind of pitch comes across the plate and is sensed by the ultrasonic sensor, the Arduino processes that information and then sends it up here so that the servos will turn in a certain way to throw the next pitch in a certain manner. On top of the servos, we have our flywheel drivers and our flywheels, which are hooked up to batteries and switches of their own, which allows us to turn them on and off so we're not wasting battery life. And then, so those flywheel motors aren't controlled by any code, but the rest of it is. So this section here basically just allows us to contact the Arduino servo library, which is a specific set of instructions specifically for this kind of motor. We connected all the servos to everything. There are notes in here about that. Then we started command with the computer, attached the servos to pins, and then connected our distance sensors. And then for our loop thing, this entire thing here is just saying, hey, read it out in inches. Read out the distance between the ground and the bat or ball in inches. And then this allows us to define our strike zone with these measurements here. So it's between 20 and 72 inches and the width of the plate, which is what the sensor does. And then if the ball or bat comes through the strike zone on a certain kind of pitch, it'll go here and turn the servos to throw a curveball. If the strike is not thrown, and then it'll come through as a fastball on the next pitch. And then it has a 4-second delay to let us set up the next ball. So, as we stated a minute ago, our machine aimed to combine the best elements of a human pitcher and the robot pitcher. A robotic pitcher can just go forever and forever all day long, versus a human pitcher has a brain and knows what pitch selection would be best for this current situation. So by applying that baseball IQ to our Arduino, we enabled our pitching machine to kind of take over the human element of it and fully automate itself. The machine knows whether or not a strike or ball was thrown based on sensors located around home plate, and then home plate has wires running back into the Arduino. So it uses the system to figure out whether or not it was a ball or strike, and then it calculates with that what the last pitch thrown was, the result of it, and then figures out what the next one should be, all in a matter of seconds.
In summary, we created a machine that automatically varies the pitches based on the type and result of the last pitch.
Basic pitch is cost-effective, safe, and a fun way to improve your game.